Okay, good morning. In the previous lectures, we have discussed how to collect data. That was using APIs, that was through scraping. After we have collected data, we looked at, is the data correct? So we did things like validation. We did things like cleaning. We also looked at different formats in which the data is generally available. So this includes JSON, CSV, XML, different formats depending on the different requirements. Today we are going to move ahead and see if we can just stop there after we've done the validation. Is that enough? Can we now build our AI and ML products, or do we need to do something else also? We've looked at a table which is perhaps something like this. We have the title, the year, genre, runtime, director, and the budget. And we may have, let's say, a database of 10,000 odd movies. The question is, can we build a model right now, or are we missing something? Remember, our goal was to try and predict the revenue. Now, where does the revenue come from? If we are talking about movies, if I have to tell the revenue of a movie, what all sources can I get a revenue from? One, the default one would be theaters. Right? So you have to account for theaters. But what about theaters which are outside the country? What about some regional theaters? What about the movie which is being shown with a different, let's say, language? What about where it's shown slightly differently or something which is off the charts? What about streaming deals? What about DVD which have been sold? So there are all these different fields which we need to, this is all the different data which we need to somehow get, aggregate, and then get the total revenue. So the important thing to note here is that once we have even got the inputs, we want to use the movie name, the year, genre, budget in order to predict the total revenue. But we need to get the ground truth or the label for the total revenue. And we've discussed that it's not trivial to get. We need to get it from different sources, including domestic, international, streaming deals, etc. Now, each of them will also have their own set of reporting standards. Let's say that the international box office you get is perhaps in US dollars. We're talking about a movie in India, let's say. We're getting the international box office details in US dollars. Now, there would be again different factors you need to look into. Is the dollar to rupee rate the same every day? No. We have to perhaps account for that. Similarly, for streaming deals, perhaps the deal happened sometime earlier, later, so you have to account for all those factors. So eventually, let's say that we are able to create this kind of a database after a lot of manual intervention. We could have also predicted different kinds of things. We were looking at the total revenue, but we could also predict, let's say, the critical success. We have these critics on Rotten Tomatoes, Metacritic, IMDb, as well as for the Indian movies, you might have seen that they have the, let's say, Times of India critic or the Hindustan Times critic or the Hindu critic, something like that. So let's say that each of them give a score. So now your task is, can you predict the score of the critics given a movie? So now you have to again get the critic scores from somewhere, you have to aggregate them in some way. Maybe all of them are not on the same scale. So again, you have to do a bunch of things to get the labeled data, which goes beyond just what the data you had collected in week 1 and 2. So therefore, today's class we are going to look at the following questions. Where does the unlabeled data come from? What is the difference between labeled and unlabeled data? What are the different types of labeling tasks or different types of AI machine learning tasks? How do we label the data, which is tools, platforms? Once we have done the labeling, are we sure that the labeling is done correctly or not? And then how do we manage the guidelines for annotating or labeling the data? It's beyond 8:35, so the TAs can ensure that no one is now allowed to enter the class from across the different doors. So this is the main problem which we need to tackle today. We have a lot of unlabeled data. So think about Flipkart or Amazon, how many reviews do you think they might have? On the order of thousands, millions, billions, huge number of reviews. How many of them have been labeled, let's say, positive, negative? A very small subset, maybe even none. So if you open a random website, if you look at the reviews, they are not labeled, this is a positive review, this is a negative review. What about call recording? So how many of you have been on IVR systems where they say that this call may be used for recording and training purposes, and please consent to this? Yes, perhaps everyone? Now how do you think they will use this call for any training and validation purposes? Any guesses?
Maybe for the purpose of the call, like if the call is made for, like before you call, you get to choose like what is the purpose of your call. Is it to complain or is it just a normal feedback?
Okay, good. So categorization of the intended task, whether it's a complaint, whether it's a feedback, whether it is you want to disconnect from the service. Yes, there was another answer there. Extract the relevant information, perhaps what menu they wanted to use in the IVR, for which they had to speak to a customer representative. Yes.
Your feedback would be used for reinforcement for the model.
Okay, so you want to somehow get a feedback of whether the client was happy or not. So maybe that could be a binary task, whether the purpose was solved or not. So therefore, there are these different kinds of fields which we need to somehow extract. Let's talk about the CCTV cameras. So they are always monitoring 24/7. Now so that is just the unlabeled data. That's just the raw video data which is available. Now if you have to get something meaningful out of it, perhaps you want to understand when there is some car passing by. So then you'll have to note the exact timestamps at which a car is passing by. That is not present. You'll have to do the labeling. For any video, for any IVR call or any other call, customer representative call, you have to have someone who labels whether this purpose was solved or not. For a review on Amazon, you have to have someone who labels whether this is a positive review, negative review, sarcastic review. Medical scans, you have to have a doctor or have let's say, a radiologist look at the report and tell whether this person has pneumonia or not. Tweets, you again have to tell whether it is pro or it is against certain kind of phenomena that we're talking about, positive, negative, neutral. So the important thing to learn here is that unlabeled data is available very easily, which is what we have thus far seen, but getting the labels, getting something meaningful out which we want to predict is hard. So we've looked at a few examples, e-commerce, call centers, security, hospital. You won't be surprised there are companies which create these labels, who have a lot of products for creating the labeled data. And the last statement is an important statement. Labels are sometimes more expensive than the collection of the raw data itself, because you need some kind of an expertise in that. Now, if you want to go from unlabeled data to the labeled data, you have to have some systems, which is the labeling process, where you have to invest some amount of time, money and effort, each of which is a very valuable, very scarce resource. So therefore, we'll see that what is the labeling process, how can we optimize it, how can we ensure that the labels are correct for the data that we have collected. For today's lecture and for the lab, we'll be using multiple tools, one of which is going to be Label Studio. I'll show the interface in a bit. It supports putting labels across multiple modalities of data, including text, image, audio, video, and we'll see it in a bit, how this works. Before that, we want to understand the different kinds of labeling tasks and how we can represent the labels. So let's go to some simple text tasks. So text classification. The first kind of task may be perhaps given an email, you want to tell whether it is spam or not. So here your labels would be one of two. It would be either spam, not spam. So it is not a very difficult task. This is the first kind of a task. Second, slightly harder, sentiment analysis. You have a review from Amazon, on an Amazon product, you want to tell whether it is positive, negative or neutral. Third named entity recognition. So perhaps if you have given a statement, Tim Cook announced iPhone in California, you want to label that Tim Cook is the person, iPhone is the product, California is the location. So you're trying to get the different categorization for each or of the different words, and the different person, product, locations are what you're trying to figure out from a given sentence. Question answering, if you're given a huge sentence or a pile of, let's say, encyclopedia articles, you ask a question, you want to get the answer. And relation extraction, you want to be able to tell things like Steve Jobs founded Apple. Here, founded is the verb which you're trying to figure out, given a sentence. So each of them, you're going from left to right, you're taking the task complexity from simple to complex. So we need to figure out how to get the labels for these. Similarly, there are vision complexity spectrum tasks. The first task could be given an image, classify cat versus dog. Simple, two outputs. Second, you want to detect a box, you want to draw a box around any object that you're trying to detect, maybe around cars, maybe around trees. Third, key point detection. If, let's say, you want to detect some important key point, let's say the elbow joints, the wrist joints. Then you have something known as segmentation. Here, you're drawing pixel perfect masks around the objects of concern. Instance segmentation, not only the semantic segmentation previously, but you also color different instances of the same object differently. These two persons have been colored differently. Now again, as you go from left to right, the amount of effort required for annotation increases. We'll go in detail about each of these, but this is just a very quick overview of the different kinds of tasks. Audio, first is classification, whether this is music versus speech. More complex, transcription, given an audio you want to transcribe into text. More complex, speaker identification, whether it's person A, person B. Sound effect detection, you want to detect dog is barking or the gun has been shot. And diarization, where you're also looking at more sophisticated who said what and the speakers and the emotions, you're trying to get all of them. Now again, if you have to create the labels for them, again as you go from left to right, the labeling process gets more complicated. Sometimes in this case, for a 1 hour audio, you might end up taking 10 hours for the annotation. So therefore, audio annotation can be much more expensive. For getting the audio data, you just need to hook up a mic. For getting the labels, you'll have to have a human being look at it, look at the audio very carefully, label where this person started speaking, stopped speaking, exact timestamps. Similarly for video, you can have a clip classification, whether it's sports or news. Temporal segmentation, given let's say a cooking video, you want to tell where was the ingredient being added, where was the dish being washed, etc. And dense captioning, which is the most sophisticated one. Given a video, you want to be able to generate the entire caption, describe what is happening in the video. We'll first start with the simplest categories which we discussed, just binary classification, which means our output would be either spam or not spam in this case. So this is how our inbox might look like. So how do you think systems are able to figure out whether something is spam or not spam? Your Gmail does a fairly good job at identifying spam and not spam. How does that work? Keywords, okay. If you have words like lottery, it is maybe a spam. Okay, that could be one category. What could be others? Sender, whether the sender is known or not known. Where is it coming from, etc. So you have to look at all those input features, but today we are talking about labeling. So again, you'll have to have a human expert. At this stage, we're talking about human experts who will look at these 10 emails, tell which of them are spam and not spam, and mark those. Once we have that marked, we can then feed that label data to a machine learning pipeline. So the way we'll think about this is, now, does this look familiar, what we're seeing on the screen? This is a JSON representation for the different kinds of text classification tasks. So let's say you're given a text where the key is the text, you want to give a label which is negative. The movie was terrible, you want to assign one of the two labels, positive or negative. So you can assign this JSON-like structure. Now you can also have multi-class classification. This is, let's say, for a support message. How do I reset my password? So you want to tell whether this is account support, billing, technical, sales or other. So the output, the label can be one of the K classes here. Multi-label classification, which is you can associate multiple labels with any given sentence. Great phone with poor battery. So this has a positive feature as well as a negative feature. The negative feature is the poor battery, the positive is the great phone. So the reason I'm showing you this is we have to somehow feed something like this to a machine learning model, which is structured information. Yes, there's a question.
But why doesn't it tend towards the neutral response in the last one? Neutral feature.
No, so this is about, we'll see this in a minute. This we are talking about, this can be just an example. So this is the reason why we are discussing today. Different annotators can view the same message differently. I maybe thought this is positive feature, negative feature. You as another annotator who is labeling this data, you might think it's neutral. Now how do I resolve this? This is where we will discuss towards the end of the lecture something which is known as inter-annotator agreement. If two annotators or multiple annotators disagree, how do we come up with a final label? This is bound to happen. Humans will have disagreements. So do you think this is a nice interface if I have to create this huge JSON? Yes? No? This is perhaps still okay given the current task, but we may want to have something like this. You have a sentence or a review, and then you have to do a radio one of the K classes check, positive, negative, mixed, neutral, and then you click submit and then you move on to the next. Isn't this better? Let's see if our tool Label Studio can provide something similar or not. So this is the interface that we have ended up creating. The script was awful and the characters were unlikable. So I have a set of questions. I have a set of these reviews. And I've created these three different classes, positive, negative, and neutral. So the script was awful and the characters were unlikable. This is perhaps negative. I can either click here or I can just press 2, which is for this particular option. I'll press 2. I'll press Command Enter, or I'll just click on. I'll move on to the next one. So once I do this for all the movies, I can just perhaps do submit and exit. I can then do an export and export this to a JSON or a CSV or a JSON minified or a TSV. There are different formats in which I can export this. Let's say I want to export this to a JSON and a new folder called So this is how the JSON might look like. This perhaps doesn't look too useful to you. So let's just render this in JQ. Right, so this was the JSON that we had created. Now you can look at, this is an ID of a sample. We have annotations created by an ID of an annotator. So you have multiple annotators perhaps. And then the answer entered is negative. We created ad, updated ad. We can also see the specific time someone created a comment. So this is how eventually the JSON will get created. This would then be fed into some machine learning pipeline. Now this interface very nicely also allows, if you have multiple annotators who have answered, who have annotated a specific sentiment in this case, for a, who have marked the sentiment for any given example, you can see all of them. So the total annotations in that case will be 2, 3, 4, depending on the number of annotators. So this was to show for text classification. This is how we can create such kind of a tool. So importantly, if we want to understand how this configuration is done, so we can just perhaps, so this is the XML which we need to create in order to see, in order to tell that these are the 3 options that we want to give. There are different kinds of tasks which Label Studio allows. So if you have to create a new task, we will be starting with perhaps something like create a new task. Let's say it is classification. And for now, I'll skip the data. I think it won't allow me to skip the data. Eventually, if you'll go here and the settings, now you see that we have not really specified what kind of a task this is. We can choose template. Maybe from natural language processing, we want to do the text classification. Now it gives the option as positive, negative, neutral. Maybe you want to change this neutral or just remove it. You can save it. This will now be the 2-class classification problem that we're trying to solve through this Label Studio interface. There was an option to also import the data, so that way you can import the JSONs, the CSV, etc. The details we'll do in the lab. Similarly, now we have trying to extract information from clinical notes. So here you want to get information like the drug names, dosages, symptoms. You want to label that automatically. So the solution which we will be looking here is called named entity recognition. Given the text Apple CEO Tim Cook announced iPhone 15 in Cupertino, we want to have these entities, which is Apple is an entity which is organization, Tim Cook, which is from 10th to the 18th character in the string. Apple is from 0 to the 5th character. iPhone 15 is the product from 29 to 38th character, and Cupertino is the location. Eventually, you want to create a JSON format like this. Given this text, these are the entities. Start 0 to 5, label is organization. Start 10 to 18, the label is the person. This is how you can create a JSON structure which you can then feed to the machine learning pipelines. Now, this is perhaps what we might want to see from a labeling interface. Let's see if our interface provides something similar. So, we go to named entity recognition, and let's say we go to this. So, Microsoft founder Bill Gates visited the World Health Organization in Geneva yesterday. We want to label the person, organization, location, date and product. So, maybe the person we want to label is Bill Gates. The organization which we want to label is Microsoft. The location is Geneva. I don't know whether we should be putting Geneva, World Health Organization, Geneva. Let's just put this. Product, there is no product. Date is yesterday. So, this is how we will end up creating these different fields. Eventually, this will similarly create the JSON which we looked at earlier. So, it will have a start, end, character, position in the string, and then the specific entity, entity category, person, organization, location, date, product. Now, once we do this annotation, again because we are talking about data annotation challenges, we will see that there can be a lot of ambiguity. So, if we write New York City Mayor, and if you want to label the city, is it New York, is it New York City? Again, we can have some amount of ambiguity between the different annotators. We can also have nested entities. If we say that the MIT AI lab director created this new interface for labeling data set cleanly, now the organization, should it be MIT AI lab or whether it should be MIT, or should you be giving a hierarchical representation? Again, it's something which we need to think about. Overlapping context, Bank of America. Are we talking about the organization, which is the Bank of America is the name of a bank, or are we talking about the location, the bank which is situated in America, Washington, are we talking about Washington as a person or Washington as a location? So this is where we lose out if we do not have very clearly defined guidelines for annotation as well as handling a lot of edge cases. We looked at this problem earlier. We have looked at the feedback either on, let's say, booking.com or amazon.com like websites. Terrible service, apps keep crashing, it is okay, does the job. So we want to figure out how many of people are finding the service positive, negative, what kinds of complaints are commonly coming. We want to create a dashboard of sentiment analysis. So we can have this at two levels. The first being at a document level. Given a document, great movie, loved every moment, you can associate a sentiment with it, which is in this case positive. You can also have a sentence level sentiment. Great visuals, poor story, this is the text. You break it into sentences, which is a list where the first element is text, great visuals, the sentiment is positive. The next is text, poor story, the sentiment is negative. So again, depends entirely on the kind of task that you're trying to solve. But importantly, if you're noticing, for each of the tasks we're looking at, we're either looking at some JSON or some CSV like structure where we can create the labels, which we can use further. We can also have sentiment on a per feature basis. Can the student be, please? So we're looking at sentiment per feature or the aspect. Great camera, poor battery. Now you can have a single line which tells whether this is positive, negative, or you can have aspect was camera and the sentiment was positive, or the aspect was battery but the sentiment is negative. So therefore you have to see the task, based on that do the annotation. Again, sarcasm is what makes life difficult. Yeah, great service, 2-hour wait. Now if you have a very naive reviewer or a machine learning or a, let's say, very simple machine learning model which is creating the reviews, they might think this is positive, but clearly this is negative because this person is making a sarcastic remark. Mixed sentiment, good product, terrible delivery. What is the overall take? Is it positive, negative? Here again, perhaps if we had feature level or sentence level or phrase level analysis, that might have been better, but it gets more expensive. Neutral versus no opinion, sometimes the phone is blue. People might say something like this. Now, is that a positive? Is that a negative? Is it factual? So we have to have clear guidelines on how to do the annotation for such cases. Similarly, we have relation extraction. Given a text, Steve Jobs founded Apple in 1976, we have to create the entities and the relationships. So the relationships can generally be thought about as triplets. Person, founded, organization. Organization, founded by or founded in year. So you have to think of triplets where you have some kind of a verb or something which is describing, and then you are relating the two things by that relationship. We can have similarly create such kind of interfaces and label studio like applications to do the relation extraction. Now let's go to image annotation task. Before that, any questions? All right. Let's look at how we might end up creating a JSON-like structure for different categories of image tasks. The first task is given an image, which is a photo.jpg. You want to label whether it's a cat or a dog. Multiple labels, given a scene, let's say you are seeing some mountain scene. Now you want to put different tags. This is like what you might see on Facebook, Instagram like services. You can put tags, which can be multiple tags. Outdoor, people, daytime. Similarly, if you want to create a fine-grained representation, you may want to see that if an image is dog, you want to not just tell the category, but you also want to tell the breed or the subcategory. So this is what are some of the image classification tasks and how we may represent them using some JSON-like structure or some CSV-like structure. Importantly, again, for some trivial task, For cats, dogs, you can perhaps label 200, 300, 400 images an hour, but the harder the task gets, the slower you'll get. The first task, given an image, classify into the set of categories. Let's see if we have that in Label Studio set up or not. Okay. So, is this an animal, vehicle, building, nature, food, electronics, urban object? Maybe a vehicle. So, we will label it to submit. This seems to be nature. So, the interface very nicely shows you the image and then the different labels, and then you can use the key presses from 1 through 8 in this case, and then control enter or command enter to submit. Similarly to what we had seen earlier, this would also create a JSON structure when the labels are exported. Okay. So, the classification was a simple task. Now, think about a self-driving car. The self-driving car, especially like the likes of Tesla, etc., they are capturing the data at high FPS, frames per second, and they need to take quick decisions. How do you think these cars decide when to stop, when to accelerate, when to change the lane? If they see, because the camera is perhaps seeing something like this, what do they need to do? Do they need to classify? What do they need to classify? Okay, so let's first come to classification. The classification task could be, are there people or not? That could be one classification in the scene. Another classification task could be, are there cars or not? Is that very useful? That is useful, but we want to see maybe even the distance. We also want to see the horizontal span. There can be a person, but if the person is not in my lane, do I need to stop? No. So, how do I figure out where the person is, where the car is? Segmentation is a complicated method. We need something simpler. So, we will be looking at just creating a bounding box, which is a rectangular box. Now, if your machine learning algorithm gave you something like this, do you think the self-driving car could use it now? Beyond this, of course, we will have to go beyond this also to also get a sense of the depth. So, this tells you where the cars are, where the persons are, where the traffic signals are, where the intersections are, where the zebra crossing is. You will be able to label all of them. We do this via creating a rectangle. Now, how do you think we will represent this in JSON? If you have to represent a rectangle, what is the simplest way to represent a rectangle? If we just have the pixel coordinates for the two extreme corners and we know that this is a rectangle, is that enough? Or do we need to have the coordinates for all four corners? Or could we just have coordinates for one corner and also specify the height and the width? So, therefore, there are different formats in which these boxes can be stored. Now, we may end up creating a table like a JSON like this given an image. Image name, width, height, objects which are detected are, class is a car. The bounding boxes for that are 100, 200, 400, 300. So, we are giving in this case x, y, width and height, or we could also give x1, y1, x2, y2 depending on the format, either the two boundaries, extremities, or we can give starting point or the center point and the width and the height. So, there are different formats which you can use. Question to you, this image is 1920 by 1080. If another image is 400 by 600, what needs to change? If an image size changes, how can you make this still more generalizable? Yes. We can give the coordinates, the bounding boxes on a scale of 0 to 1. Maximum height, maximum width. Let's see if Label Studio can help us here also. So, we want to do object detection. Label tasks. Okay, what do we see here? Person. This is actually a very difficult example. Let me pick up a slightly simpler one. Okay, so maybe the category for this is headphones. And then I will choose a box like this. I have not drawn a very good box. I should have perhaps made it slightly wider. But I have been able to create this. Again, if you'll see the exported label, it would look something like this. Now, I just showed you a bad example. What I created was a too tight box around the object. We also don't want to lose of an object. So, we need a just right object. There are some rules of thumb. We want to skip the objects which are very small, which are occluded a lot. We want to skip the reflections. We only want to label the actual object and not the reflection. We also don't want to have very tiny objects labeled. So, these are some rules of thumb which people generally use while creating the labeling interfaces. This one seems to be an appropriate level of tightness around the box. This one is too tight, it's also missing out on some pixels. What do you think would be some downside of a too loose bounding box? Yes?
Vehicle would have to stop unnecessarily.
Yeah, so we may have to stop the vehicle very early. Another question. So we have seen here as a rectangle, as a bounding box. Could we do something better still using only rectangles? We can have the rectangles to be rotated, which would maybe in this case very nicely capture that the car is more longer than wider. So that would give you a very accurate shape of the object of concern. But that would require you to capture more input. Like now you'll also need to know the angle by which the rectangle is rotated. So these are all tasks you have to think about and their trade-offs. The next kind of task is, for example, you have to now identify certain tumors in medical scans. Now here, would it be fine to just draw a bounding box? No, the shape of the exact tumor would be of a lot of importance. We need to now know the exact size. Let's say if someone has a kidney stone, you need to exactly know the size, the dimension of that kidney stone. So for this, we end up, let me ask you before I show the solution. How do you think we can create such kind of labels? The one which I am showing on the right. How can we create such labels? Okay, what am I seeing on the right side image? Am I seeing different colors? The image, can you see that each pixel is associated with a single color? So now how do you think we can label such? How can we label for such tasks?
Some sort of pixel shading.
Yes, for each pixel you want to give a single color, right? So if we can give each pixel a different color, we should be able to create something like this.
We are still only using humans for labeling, right?
If you're using,
We are using humans for labeling, right?
we are generally using humans for labeling. For such difficult tasks, we may also need to have semi-automated systems where we have AI-assisted labeling. AI-assisted labeling is very, very good these days. If we look at some tools like Segment Anything Model, SAM, as well as their overlaying the interfaces such as RoboFlow provides a few interfaces. And given this particular photograph that we're seeing, we perhaps want to create this segmentation mask where you want to separate out the buildings, the sky, the other kinds of buildings, the car and the person. So the task would be to look at each pixel, label it to be any specific K classes. So this is much more expensive than the bounding box, if you noted. So therefore, for this, one way to think about this is you will create multiple images. Given an input image, given this input image, you will create multiple images which consist only of zeros and ones. The first image puts a 0 wherever puts a 1 wherever we have a sky, puts a 0 everywhere else. Next image puts a 1 wherever we have a person and puts a 0 everywhere else. The next image puts a 1 wherever we have a car and puts a 0 everywhere else. The next puts a 1 wherever we have the buildings and 0 everywhere, so on. Then if you have created these multiple images, you can then compose them to create this overall segmentation mask. Any questions on that? Now, when we talk about segmentation, we generally think in terms of two kinds of tasks. One is just semantic, like label every dog as a dog category. Second, you also want to give them numbers. Why do you think the latter might be important? What might be the utility of instance segmentation versus semantic segmentation? Counting you can get via semantic segmentation also. The dog could be of different breed. Okay. Say I want to track one specific dog's behavior over time in a video. Then I would need the identity of that. Now, so I mentioned one particular format of storing a mask, which was pixel wise you create 0, 1 multiple images. Another method which is similar to what the bounding box method was, you create this kind of a high number of sites polygon. How many of you have used something like Photoshop? Does this remind you of the pen tool? You're trying to create using, so you click multiple times. You'll be able to create something which looks fairly good, almost the same level of tightness as the pixel level one, but this is easier to do. The other advantage of this is vector based, this is pixel based. Each and every pixel has to be labeled. Here you are creating this high dimensional, this high number of sites polygon. When we look at applications for this, you may also want to look at perhaps satellite imagery and do things like urban planning. Given an image, you can identify the rivers, the water bodies, the green cover, etc. Next kind of a task. Someone is recuperating from injury. You want to tell, or for elite sportsmen, you want to figure out whether they're doing exercise correctly or not. Think of this as, and I'm pitching this as a startup idea if anyone wants to build on this. You have a smart TV with a camera in front of that. You do your exercises. The TV will now not only show you how to do the exercises, but it can, because it has a camera, it can actually look at you and figure out what are you doing correct and what are you doing wrong. In order to do that, it needs to figure out the position of the different joints, the different orientation that you have in the body. So for that, we end up creating this kind of an interface where we do the key point detection. Where are the shoulders? Where is the elbow? Where is the wrist? Where is the knee? Where is the ankle? So on. Again, if you have to represent this, again a JSON. So throughout this lecture, I think you should be able to appreciate the fact that any complicated machine learning task that you're looking at, any complicated such similar kind of a task, labels are in some specific format, each of which has a certain connotation associated with it. In this case, for example, the nose, left eye, left shoulder, right shoulder is something which we already know, we have defined as a meaning, and then we tell the locations for that. It's a pixel that we're defining. So folks who are using their phones to play games, I am seeing you. This is a warning. We also looked at in Label Studio that these are the different kinds of XMLs which we'll create. This is the XML which we created for classification. We give the choices as positive, negative, neutral. We can also give for named entity recognition, which was the person, organization, location, date. Importantly, here we also give the colors to make it slightly easy for us to do the annotation. We can give for object detection. Importantly, here we have to specify that it's rectangle labels and the bounding box format. And the classes that we have are car, person, bicycle. We have similar other tools which we'll do in the lab. Okay, before we go to the next part, questions? Thus far, we have still not studied how would a machine learning model take these labels and the input data and do the learning. So that we have to rely on a machine learning course. In our course, we will not learn that. We will briefly touch upon this to ensure everyone is on the same page. But importantly, we now want to understand that I should, as an annotator, I've marked certain labels. But is that correct? How do I know whether that is correct or not? What do you think? Another annotator. But I just annotated everything. Am I not your instructor? Am I not supposed to know it all? No. Different annotators will make mistakes, different kinds of mistakes, and different annotators will cost you different amount of money. Let's say if I have to get a bug fixed in Linux, if you come to me, I will probably ask, let's say I need 10,000, 20,000 rupees a day and I'll fix the bug. If you go to Linux Torvalds, how much amount of money may he charge? Much more. So different experts have different value that they'll bring to the labeling process, to the correction process. So that is also something which we need to consider. But importantly, we want to go beyond a single annotator. We want to go to multiple annotators. This is the classic example. One human might say this is a duck, the other might say this is a rabbit, and both of them would be correct and both of them would be wrong, depending on the view that we want to take. So what do you think? Is this a duck or is this a rabbit? Yeah, but your machine learning model will not be happy to know this answer, features of both. It needs to know something. How can you resolve this ambiguity? Remove the image? No, this image will remain. Let's say this image has to remain. Okay, if I ask you this question, is this a duck or is this a rabbit? You're confused. Let me ask this question. Look at all images going from left to right only and give precedence to the left to right view of the image as opposed to from right to left. Now what is your answer? So does the guideline help you with a more consistent answer? In the absence of that, you will end up creating a lot of very wrong answers. The errors will only propagate more southwards if you don't give the correct kind of annotation guidelines and thus do not have the correct labels associated with the images. There are different kinds of disagreements. How many of you been to, okay, let me ask this question. Why do people consult multiple doctors? Especially for more sophisticated cases. So they consider, so even among specialists, sometimes people may go to 2 or 3 specialists. Why? There might be a bias. Different doctors may have different subjective understanding of your case. And then some people might say you need a surgery. Some doctors will say you don't need a surgery. And then you have to finally take some kind of a collective decision based on the inputs that you're taking, based on your intuition, based on your understanding, based on the doctors, their past experience, all of those factors. But the important thing I wanted to mention was that Given an X-ray, different doctors can say that this person has pneumonia, doesn't have pneumonia, has COVID, doesn't have COVID, needs to have a surgery, doesn't need to have a surgery. So therefore, we can have disagreement even amongst highly specialized workers such as, let's say, specialist doctors. Sentiment not bad for what it is. So I hope this joke doesn't go the wrong way, because there might be some audience outside of India also sometimes. So sometimes in different contexts, if you ask for a question, so I've been asked this question in the West, how are you doing? I thought that the other person was genuinely asking me how my day was going, etc., all of those things. So I started answering. I did this, I did that, I did this. After a while, I realized that in certain Western contexts, this is just supposed to be something like a hi or a hello. And then I could realize why the person asked this question and was getting impatient when my answer was long. Similarly, in certain contexts, if you ask a question, how are you doing? So they may say not bad at all or something like that, not bad for what it is. So not bad at all in some cases is a meaning for it's quite bad. It's a very mild way of saying not bad. Oh, it's quite bad, not bad at all. In certain contexts, we might think, okay, not and bad, which means quite good. So we have to again have a subject of local context associated with the task, as well as understand the sarcasm. So the part which I was mentioning was cultural. Spam, newsletter from a store you signed up for. Let's say if you want to buy certain clothes, they send you a newsletter, you're actually interested in them. But 90% of the newsletters you're not interested in. Political criticism, which is a very common topic, whether you are party A or party B or party C, what is your affiliation? Based on that also people tend to assign labels. The unfortunate bit about the bad labels is the chain reaction. If the task is not clearly defined, which is, as an example, the rabbit versus the duck, the annotators will interpret differently. They will create inconsistent labels. The models will learn conflicting patterns, and you will end up creating a model which does very poorly. So therefore, we need to correct this at the first step itself. Otherwise, the errors will only propagate downwards. Let us take this example. You have two annotators. We are asking them to label this binary classification task, whether it's a spam or a not spam. We have 5 records. Annotator A says spam 3 times. So now we have a little bit of maths. So please wake up if you were sleeping till now. Annotator A says spam in ID 1, 3 and 5, 3 out of 5 times. Annotator B says spam in ID 1, 2 and 3. Overall, out of the 5 cases, we have an agreement of 3 cases, 3 times they agree. Is this a good agreement? Yes? No? So whenever asked such kind of questions, ask more questions. Because whenever such questions are there, we need more context to give a well-rounded answer as opposed to a very generic answer. So let's look at the cases. Annotator A said spam 3 out of 5 times. Annotator B also said spam 3 out of 5 times. So based on this data, if we were to say probability that both of them would say spam, if we perhaps had a larger database, the probability both of them would say a spam is 3 over 5 into 3 over 5, or 0.6 into 0.6, which is 0.36. Probability that both of them would say not spam would be 2 over 5 for A and 2 over 5 for B, which is 0.4 into 0.4, multiply both of them, you will get 0.6. So the probability that both of them would agree by chance would be 0.36 plus 0.16, which is 0.52. And the agreement that now they have observed is 60%, which is only marginally better than the 52% they could have agreed by chance, given their historical, given the history of their preferences of labeling spam and not spam. So in that context, do you think now the 60% number is good or bad? not very good. So therefore, we can have multiple metrics to tell whether the annotators are correct or not. This one is the simplest one, which just looks at the overall agreement. But unfortunately, it does not count for the performance if there was a randomly done experiment and we looked at their agreement by chance. To understand this better, let's look at these 10 examples. So forget this random guessing for now. We have these 10 examples: spam, not spam, spam, not spam, spam, not spam. So can you now work out it in your notebooks and tell me what is the agreement that they have? The agreement is trivial, the next thing is harder. How many examples are they agreeing on? 8, first, second, third, fifth, sixth, 7th, 9th, and 2 examples they are not agreeing on. So their agreement percentage is 80%. Now tell me, if they agreed by chance, what would that number be? Do the calculations similarly to the way we had done previously. Probability A says spam, probabilities B says spam, probability A says not spam, probability B says not spam. And then figure out both say spam, both say not spam. Add them up and tell me the chance probability, the chance agreement. Point? So 6 spam, 4 not, A says that. B also says 6 spam, 4 not spam. So therefore, the probability both say spam is 0.6 into 0.6 plus 0.4 into 0.4, which is 0.52. The observed agreement is 0.8. Now somehow we have to come up with a single metric which combines both of these to give you a single number, which is known as the Cohen's kappa score, which is to say that how much better than chance is your agreement. So you do P observed minus P expected divided by 1 minus P expected. If we look at this formula, the kappa score, the P observed is what is the observed level of agreement, which is 0.8, minus the expected level of agreement. The expected level of agreement just comes by the chance. So just by looking at the proportions, the expected level of agreement is 0.52, and then you do 1 minus 0.52, which gives you an overall number of 0.58. Now do you think this is a very good number? No. So this is how you need to contextualize the inter-annotator agreement. You have to look at the performance of what the random was giving you already, and the random agreement was giving you already. Now once you take that out, so you, in this case you are doing 0.8 minus 0.52, that is the improvement that you are getting over chance. The maximum improvement that you could have got over chance was 1 minus 0.52. Right? So think of this in this way. Chance is 0.52. So therefore the maximum you can get beyond chance is 48. Now out of that 48, how much are you able to get via your annotators? That is 0.8 minus 0.52. So that is 0.28. 0.28 over 0.48 is 0.58, which tells you how much better than chance are your annotators are. And if you were to run this through scikit-learn and give these two arrays, you'd be able to get the annotation score of 0.58. Now there are multiple extensions to this, which I am leaving for you to think as homework and for the lab. The questions, think of these questions. What if we had more than 2 annotators? Right, that's one question. Next question, what if we had more than 2 categories? Here we have spam, not spam. Think of if you had 3 categories, 4 categories, how would you extend this framework? In terms of the general interpretation guide for kappa, we mentioned that we typically want something above 0.8. 0.6 to 0.8 is also considered good. So therefore, 0.58 was almost there, but we needed some more improvement. I am also giving you the hints here. 3 plus annotators, categorical, Flay's kappa, and multiple categories also you have to think about that. How would you modify this specific formula to account for that? Now, when we think about other kinds of tasks, such as bounding boxes, I produce the bounding box, you produce the bounding box. How would we say that the annotations are correct? We'd have to look at the 2 bounding boxes or the bounding box between me and the ground truth. At the time of prediction, I do that. This particular metric is known as IOU, intersection over union. Here, assume that box A, which is shown in blue, is the correct box. So the metric I am showing you is used in 2 contexts. One, to tell how good my machine learning model is doing. Second, if I have 2 annotators, how much are they agreeing? So in this case, I am showing the first case. The blue is the true box. The red one is what my model has predicted. Now, in the ideal case, the intersection between both of them would be very high. But can you tell me of a counter case where I can have intersection of 100%, but still the box is not good? Let's assume that you had box A, which is the blue one, to be completely contained inside the red box. In that case, the intersection would be the blue box. The intersection is 100%. But the red box you have predicted to be very long. So let's imagine that if I have to, in this setup that I am seeing in front of me, if I have to label the screens or just one screen. So a very tight box would be if I draw a box around the screen which I am seeing. A very bad box would be if I draw the entire screen as my prediction. What is the intersection between these two? Still that specific thing which I am labeling. But is this a good prediction? No. How can I improve my metric now? I have to also look at the union of the two. So I am looking at intersection over union. The union will tell me the area contained in both the boxes, and the intersection will tell me the area in the commonality of the boxes, the intersection of those. That ratio I want to be as high as possible. So therefore, this is intuitively just known as intersection over union. So I think in the lab we will be deriving this from scratch. Should be a very simple function. You just need to look at 2 rectangles, figure out their areas, intersection, unions, etc. So typically we want to say the IOU greater than 0.7 is considered to be good. Many of these things are rules of thumb which people have been using in the industry. Similarly, for segmentation, we can do the same thing. Now, instead of having the boxes, you will have these complicated shapes, either polygon masks or pixel-wise masks. But importantly, you can again look at the prediction and the ground truth and figure out the intersection over the union. There are other metrics also, such as the dice score. We will not talk about this now, but it's quite trivial to implement again these. Where? Yes. The union should be greater than 0. I think this would perhaps be the case when, if the object is not detected, I don't know. Maybe if that's the case. I don't know, this seems to be some corner case. So therefore, if we were to categorize these numbers, again, some rules of thumb. Don't take them that if it's exactly this, then my labeling is good. It may again depend on the problem at hand. So text classification, we look at Cohen's kappa. Similarly for sentiment analysis, for other kinds of tasks like named entity recognition, we can also look at the another metric which is similar to accuracy known as the F1 score. Object detection, we are looking at IOU, intersection over union, similarly for segmentation. For transcription, we are looking at things like the word error rate. What is the error in the words between the different annotators? And each of them have typically some notion of what is a good inter-annotator agreement. Finally, we'll end by discussing the 6 pillars which make the annotation better. First, we need to have very clear guidelines. So we have looked at a few bad guidelines and a few good guidelines. The definition should be clear as well as the edge cases need to be told. There is sometimes we do a pilot annotation, which is we just label 50, 100 images or objects or samples, and then we see how people are doing. In some cases, another kind of a method is that if I ask you to label 50 to 100 images or objects or instances, I keep some images which for which I know the correct label or the ground truth. I still give it to you, and then I check whether on those what is your performance, because on the unknown I don't know the ground truth also. I will artificially inject some examples, which is the third point, gold standard, 10% known, correct items are mixed in. So on that basis, we can figure out, are you able to correctly get even the gold standard images or objects or not. We often end up getting multiple annotators per item, per sample, and we also try and track the inter-annotator agreement over time. Why might you think the inter-annotator agreement might change over time?
As it sees more images.
Okay, so if you play a video game, do you get better over time? Yes. So even the annotators might get better over time once they figure out. That could be one way, positive direction. What could be something else which changes the inter-annotator agreement over time?
Maybe they encounter some new case or some new sort of label, so they have to.
Okay, so there is perhaps some new information which they get, which changes their views.
Maybe the images that are now being fed are fairly easy to classify.
Okay, the distribution of the input itself changes. Good. What else could change? Maybe the guidelines have changed, but many of them might poke you in the positive direction. What might poke you in the negative direction?
Maybe some annotator working from very long time.
Exhaustion. People get tired. People get bored. What is this same task I'm doing again and 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 again? Let me just put them under the shrug. No one will even know. They might even think there are 3 annotators. Even if I make a mistake, someone else will probably do it wrong or will do it correct. Who knows that the other 3 are also thinking in the same way? And then the label data gives you 50% accuracy. Okay, what if you had 4 annotators? For some reason you chose 4 annotators. 2 said yes, 2 said no. What will you now do? You may need to go to an expert. Sometimes you may do a majority vote. Sometimes you may need to go to an expert who can then decide which of them is correct. So this is also one example which we'll also see in the upcoming lectures. So let's say if we have some samples where a lot of annotators are disagreeing. Those are good samples to be sent to the expert. What do you think this answer should be? Some questions you might think for interviews. How do you ensure label quality in large annotation project? You may want to talk about multiple annotators to give the redundancy. You may want to have very clear guidelines, gold standard questions for monitoring, some calibration sessions. So calibration sessions is you look at the performance after the pilot. After that, you retrain the annotators and tell them perhaps you labeled this wrong. So let me just explain the guidelines again. Wattens, Cohen's, kappa. You might find it surprising that when we generally think in terms of the inter-annotator agreement, most people may end up just telling you the agreement, which we saw, like 80% example which you were seeing. But in Cohen's kappa, we are telling what you can get by chance, and then the what better you can get from compared to the chance. The takeaways, I know you might be a little disappointed to see this 80% number crop up in almost every slide. So this often comes up because different people say that this thing takes up 80%, this thing takes up 80%. So someone somewhere has always said that this specific thing takes 80%. But getting the labels is actually hard. Different tasks, we need to understand what is the way we represent the labels. They also bring in different amount of challenges. We can start with simple free tools such as Label Studio for doing the annotation. We need to measure the agreement amongst the annotators by measures such as Cohen's kappa. We may think that guidelines are a waste of time, documentation is a waste of time, but eventually they'll save you a lot of time, because otherwise later when you'll see that on these samples your performance is bad, that was because the labels were wrong. Quality control is not a one-time thing. You have to reinvest in it. You have to periodically monitor it. And we have to be realistic in getting the budget for domain expertise. There are also various tools when you talk about budgeting. There are various open source crowdsourcing platforms which can help you get the annotations, like Amazon Mechanical Turk, etc., where you can give these tasks and you can have a number of people on the internet sign up for a small amount of money, and then they can give the annotations. So we'll end the lecture now. Any questions? Yes.
Sir, the one problem you posed about the image having clashes between the classifiers, like two were giving S code and two were giving no code. So could we do it like that? We pass all the image training data set, and then we again pass them once the whole data set, the moderate object classifiers are moved.
Okay, so the question is that if we have some confusion between the labels, should we just have the model in the loop and then let's see the model's prediction? Sometimes people do that. They can get the model to do some kind of initial labeling, and then they have the humans check that labeling or not, whether that seems correct or not. But at this stage, we are only talking about the first pass where the humans only are creating the labels, which is creating the initial set. Whatever you've told is correct. I will also show an example of that in the coming time. Maybe in the lab we'll look at it. Okay, thank you. Please do get started on your assignments. It will take time. And pose any questions on the Slack channel.